welcome CZ to talk about Kajak.
Thank you, Barry. Hello, everyone. I'll introduce how we do the catch-up circuit. And I'm supposed to present this with Carlos, but he had he feeling unwell, so I'll do his part too. So the first thing we have to handle is the permutation part. And the permutation has a lot of bitwise operation. So we use the base conversion trick to get a sense of how the operation we need to do in the permutation. Remember that catch-up is organize the input into a state of 25 lanes, and each lane is 64 bits data. And then there are like different operations, theta, rho, and c, pi, and they need to do like XOR operations on different lanes. They need to do bit rotations on single lane. And sometimes we need to do slightly more complicated bitwise operations on like 4 lanes, or with some other constants. So naively, you kind of want to like do a pure lookup approach. For example, we have A here, B here. They are all lanes, and I have a subscription 2 for binary, and we can. But like the lookup, if you have a polynomial degree of 2 to the 16, then you can only like look up like 8 bits XOR to the 8 bits, all the possibility of 8 bit to 8 bits, and then you can split A into 8 groups, B into 8 groups, and do 8 lookups, and then add the results together. That's how naively you perform a bitwise operation on 2 lanes, but this is really inefficient. So we use this sparse space approach. So the sparse space is instead of using the binary base, we use like base 13, and then AI and BI is still bits, and then we can add the A and B together. This is just one addition in the circuit, but then we would get this thing, and we then have to find another injective mapping to map this arithmetic sum into the bitwise operation result. So the flow would look like this. The left dotted arrow is the bitwise operation lookup, which is inefficient. So instead, we convert the binary input into the sparse space, and then we have the sparse space input, and then we do cheap arithmetic operations on the input on the sparse space, and then we get the output. Then we convert the sparse space output into the binary output. So there's a general rule of thumbs. But there are some limitations. For example, the base size cannot be like arbitrarily big. So we are operating on BN curve. So you have you only have 254 bits, and so that means your base cannot be like greater than 15. And also, the larger base you use, the less chunks you can look up at a time. So it might cause some like inefficiency in the base conversion. So I try to like print some result of like if you use 2 to 16. Look up with 5 chunks. The largest base you can use is 9, But if you look up 4 chunks, the largest base you can use is 15. These are the examples. And the injective mapping is that let's say you have A, B, C, D. There are 4 bits, and then you need to perform a complicated bitwise operation like A XOR negative B and C and XOR D. You get the output bits, but you find that arithmetic linear combination of A, B, C, D, and you get the arithmetic sum of this value, but that parameter must satisfy the property that, like for example, if the output is 3, 3 always map to 1, 3 always map to 1, 3 always map to 1. Like you cannot have the same value here, but map to 2 different, like 1 or 0. So if you can find this mapping, then you can convert the output in a sparse base into the binary output. So that's a general trick in the permutation. I didn't show the detail of the rotation, and here comes the difficult part in the circuit implementation. Carlos made this awesome diagram. So at the middle of circuit, everything works fine, like with the sparse base. But like at the end of circuit, we have some branching, and that branching we took some time to figure out how to do that branching. So we need to so at the end of a permutation, we need to determine if this state is the final output, or do we need to take extra input and continue the next round of permutation. So if this is the end, then we go the left-hand side. We need to input a flag and check it's either 0 or 1. So that's a consistency. And then the left-hand side, we have iota B9. It's an operation that adds a run constant to the length. And that run constant, we need to convert it to the base 9. And then we add it to the state, and then run the base conversion to convert it from base 9 to base 2. And then we get the output state. And on the, oh, wait, oh, this is right, and this is left. OK. And right? Oh, wait. Oh, this is right, this is left. OK. On the right-hand side, we have to absorb the input to the output state, and then we convert it from base 9 to base 13, and then we add the iota, the run constant at the end of this step, because because we're reusing the previous A XOR like B and C and D. We use that D for the next input and iota, but then and then we get the output state B13, and then we need to use that flag to multiply the output and add them together to determine the real output state. Yeah, here is just a flag consistency gate to check either the flag is 0 or 1. And here's the mixing gate to combine the result from the both branch into the same output. And here is how we, the circuit is determined at the compilation time. And let's say you have, but like when in the real use case, you might have the input that require like 2 catch-IF and some input that require 3 catch-IF. Like it's determined at proving time. And how do we do that? We use the state machine approach. So we define 2 different states, absorb and finalize. And if you have, like, for example, the first hashing job has 140 bytes, and you need 2 catch-IF to process that. So you can assign the first state to absorb and second state to finalize. And then we have the second hash job that has 372 bytes, and it needs 3 catch-IF to complete the hash job. And then you can assign the first 2 to absorb, and the last one is finalized. So the takeaway here is once we define the rule of the state transition, so we can have the fixed circuit that takes the arbitrary input, but with that takes arbitrary input. And also we have the padding chips we take the last input. We actually take the input and pass through the padding chip to determine if it needs padding or not. And we take that input to the permutation chip and to get a intermediate state here. And then for the next round of catch-IF, suppose this is the finalized state, and we need to add a padding. And then we also this pre-state, we need to take the previous intermediate state and combine it with the new input to the permutation and get a final output state. And there was a part hiding on the top of the slides. Wait, do I have a way to access it? Oh. Okay, probably not. So here we have 3 columns. We have input RLC and input length and the output. So these 3 columns can be consumed by other circuit. They can look up the hash input to the hash output. So that's how like we use the catch-up circuit in the other circuit. Yeah, I think that.
3 minutes.
But okay, I can take QA or something. It's like it's the end of slides.
Oh, perfect. Any questions?
Yeah.
So in terms of how many constraints do you have for completion?
So I think that
For round, I mean.
Yeah, for a round, yeah. So the right number is 10K because it determines on the one operation that uses the most of the rows, which is the bit rotation part. And so we have to perform bit rotation for 25 lengths. And each length takes 17 rows of lookup. And then we have 24 rounds of permutations in catch-IF. So that's the 10K transform.
Okay, thank you, Zizi.
Thank you, Eric.